You know, we're always obsessed with the beginning, right? The Big Bang. But there's another question, one that's just as profound, that has fascinated scientists for a century. It's about our ultimate destiny, and that's exactly what we're going to get into.
So, how will it all end? I mean, we live in this incredible universe that's been expanding for billions of years. But is that it? Does it just keep going forever? Or could there be a much more dramatic finale waiting for us?
Well, let's start with one of the most elegant, most intuitive ideas ever cooked up, the Big Crunch. The concept is it's beautifully symmetrical. Our universe starts from this incredibly hot, dense point, the Big Bang. It expands for eons, creating galaxies, stars, everything. And then, one day, it hits the brakes, reverses course, and collapses all the way back down. A perfect cosmic bookend to the whole story.
Okay, but for a cosmic collapse like that to actually happen, one force would have to be the undisputed champion, overpowering everything else. And to understand the Big Crunch, we have to start with that force, gravity. I want you to picture the universe in this constant, epic tug-of-war, okay? So in one corner, you've got the explosive momentum from the Big Bang, always pushing everything apart. And in the other corner, you have the relentless, inward pull of gravity from every single star, every galaxy, every speck of dust. The entire fate of our universe, literally everything, hangs on which one of these forces wins.
So, this massive cosmic battle, it all boils down to one single crucial number. It's a concept called critical density. Think of it as the exact amount of stuff the universe needs to have to be perfectly balanced, right on a knife's edge. Just enough to stop the expansion, but not quite enough to pull it all back. It is the ultimate cosmic tipping point.
So for the Big Crunch to be our destiny, the actual density of our universe, a value scientists call omega, has to be greater than that critical density. It's pretty simple, right? If there's enough mass, enough stuff packed in, then gravity's pull will eventually win. The collapse isn't just possible, it's inevitable.
And hey, this isn't some brand new idea. The theoretical groundwork for all of this was laid way back in 1922 by Alexander Friedmann. He was working with Einstein's equations on general relativity, and he was the first to show that the universe's fate, whether it expands forever or collapses back on itself, was fundamentally tied to how much stuff was in it. Its destiny was literally tied to its density.
So for decades, the Big Crunch was a really serious contender. It's an elegant theory, it's grounded in solid physics, it just makes sense. But then we started actually looking, pointing our telescopes out into the deep cosmos. And what we found? Well, it changed absolutely everything.
This led to what was basically the billion-dollar question in astronomy. Can we actually measure all the stuff in the universe? Is there enough matter and energy out there for gravity to finally win that cosmic tug-of-war and trigger a big crunch? The answer, amazingly, came from some of the most violent events in the cosmos, exploding stars. In the late 1990s, astronomers were looking at these very specific kinds of supernovae. They act like these perfect cosmic light bulbs. We know exactly how bright they should be, so we can tell how far away they are. And the data they collected from these supernovae sent shockwaves through the entire field.
Now, everyone thought they knew what they were going to find. It was just common sense. The relentless pull of gravity from all the galaxies should be acting like a cosmic brake, right? It should be slowing the universe's expansion down over time. So the expansion today should be slower than it was in the past. It just seemed obvious.
But the data showed the complete opposite. The universe's expansion isn't slowing down at all, it's speeding up. The expansion today is actually faster than it was billions of years ago. This discovery was a knockout blow to the Big Crunch theory. Gravity wasn't winning the tug-of-war, it was losing, badly. So what on earth could be strong enough to push the entire universe apart against the pull of all that gravity? Well, scientists gave this mysterious thing a name: dark energy. It's some kind of repulsive force woven into the very fabric of space-time itself. It's like a cosmic anti-gravity, and right now, it looks like it's the most dominant force in the entire universe.
And with dark energy suddenly in the driver's seat, the whole map of our cosmic future had to be completely redrawn. The universe's ultimate fate no longer looked like a fiery, dramatic crunch, but something much colder.
You see, this discovery just flipped the whole script. The Big Crunch needs gravity to be the boss, but our observations show dark energy is running the show.
The Big Crunch needs the universe to have a closed geometry, kind of like a sphere, but everything we measure says our universe is flat. So all of this points away from a Big Crunch and towards its chilling opposite, the Big Freeze.
So just to sum it up, the evidence is pretty overwhelming at this point. The expansion is accelerating, not slowing down. The universe's geometry appears to be flat, and even when we count up all the matter we can see and all the invisible dark matter we can't, it's just not enough to stop this runaway expansion. All the signs are now pointing away from a fiery crunch.
So where does that leave us? It can all get a little confusing, I know. So let's use a really simple but powerful analogy to help picture the three main possibilities for how our universe might end.
Okay, imagine you throw a ball straight up in the air. The Big Crunch is like a weak toss. Gravity easily wins and pulls the ball right back down to you. The Big Freeze, which is our current best guess, is like throwing that ball so hard it actually achieves escape velocity and just flies away into space forever. And then there's a third, even crazier option, the Big Rip. That's like strapping a tiny rocket to the ball, one that accelerates so violently it eventually tears the ball itself to shreds.
And really, this brings us to the most important takeaway here. The story of the Big Crunch isn't about a failed theory. Not at all. It's actually a perfect example of science working exactly as it should. You have a beautiful, logical idea. You test it against the real world with hard evidence. And that evidence forces you to a deeper, more profound, and, yeah, a much more mysterious understanding of how things really work.
So for now, it seems our universe is headed for a long, cold, dark expansion into nothingness, the Big Freeze. But what if dark energy isn't constant? What if this mysterious force changes over cosmic time? What if it weakens and gives gravity a chance to make a comeback? The final chapter of the cosmos? Well, it may not be written just yet.